So hi, everyone. So my interest in climate, in particular temperature, which I consider to be the first vital sign of the planet, the second perhaps being ocean salinity, started when I transitioned from the private sector back in around 2005. I was working on magnetic recording materials for hard disks, and I loved the work, I loved the travel, but it was difficult to balance. Had two young children in elementary school at the time and decided to re-career into a more carbon humble teaching position. And took that opportunity to read something lighter rather than heavy technology all the time. And one of the things I read was a book called Super Freakonomics. And another thing I became aware of was some work by Ken Caldera. He's an ecology professor at Stanford, and Lowell Wood, who worked with Edwin Tiller on development of the hydrogen bomb. And that's what got me started. I also looked over my wife's shoulder, who was watching Oprah one day, and there was Al Gore. And I noticed one slide in particular looked like real scientific data. It was the Keeling curve, CO2 versus time, which I'd never seen before. And I could see the hockey stick shape, and I said, wow. So that's what got me started 20 years ago, I guess. And what I can say today, here's my roadmap. We'll definitely get through the first 2 points here, and we'll plow through the rest quickly as time allows. What I've learned is that humans definitely can cool the planet. We already have, we already are, in fact. We did it post-World War II. We're doing it today, both through smog. Post-World War II, it was Britain and the industrial heartland of the US. Now it's the eastern seaboard of China and the Indian subcontinent. Smog might look gray and dirty from below, but it's brilliant white from above, and it's reflecting sunlight, cooling the planet. In fact, it's substantially offsetting global warming. Volcanoes do the same thing. They both have a global cooling effect. So we can deliberately engineer sunlight to counter greenhouse gas warming. And I hope to lay out the physics. Now, you guys have been at some challenging coding exercises for what, 36 hours now? So I encourage you just to put your feet up, relax, and enjoy some light duty physics. Be glad to make all these slides available later if you're interested. You can work that out. So it's called Solar Radiation Management. Let's call it SRM. And I hope to convince you this is not a cost or a technical challenge. Not much has been done experimentally, not because of technical issues, but because of moral, political, ethical issues like that. I'll mention an experiment which has been on the books for several years now out of Harvard to do a small controlled stratospheric injection experiment. This was something I found in that Super Freakonomics book, which dramatizes the fact that a single 2-inch diameter hose, 8 miles long up into the stratosphere, can almost by itself cool the northern hemisphere, or maybe 2 or 3. How would we do this in practice? Well, it was thought at one point that conventional planes could fly it up. That turned out not to be the case. 747s have carburation problems up into the stratosphere. But we can use solar-powered lofting, take advantage of sunlight to warm some additional carbon black in the aerosol and create a thermal updraft. This is the same way volcanoes and, in fact, forest fires do it. The California forest fires, in fact, are injecting carbon black into the stratosphere as we speak. There are some unknowns, and I'll admit to not having much to offer as far as the ozone layer, earthbound astronomy, human health. So these two are the workings of stratospheric aerosol injection to cool the planet in theory and in practice. And as time allows, let's have a reality check on why the ideas that you're coming up with today, carbon mitigation, moving CO2, while we have to do it, it's the ultimate solution, is going to take time. I want to just elucidate some misunderstanding about the greenhouse effect. Turns out it doesn't warm the planet, but it does warm the surface. How positive feedback, this is the replacement of reflecting ice with dark seawater, amplifies the triggering effect of the CO2 by a factor of about 4. So it's not a matter of simply reducing CO2. We also must reverse this positive feedback effect. And it's going to take a long time, not decades. It's going to take hundreds of years. So the cooling gives you guys time to carry out your solutions. My focus is on the rising sea level. There are many other things that could be talked about, but the Maldives, for example, and other low-lying island nations face a real existential threat. The UN estimates by 2100, the capital of the Maldives, Malé, which is only 3 feet above sea level, will become uninhabitable. Again, these are the real problems. I've just mentioned this now. Cooling is so easy and inexpensive to do that some rogue nation or even an individual will likely be the one to initiate it. We will just see what happens. So I asked myself to get started, what determines the temperature of the Earth? And I naively thought, well, there must be heat left over from aggregation of the planet. That's why our core is molten. In fact, the core of the Earth is about the same temperature as the surface of the sun. But it turns out that's not the case. I mean, if Brandon, say, were to hold a mile-long slab of granite, and then Joshua puts a blowtorch on one end, and Brian touches the other end, Brian has nothing to be concerned about, or Brandon in the middle, therefore. Granite, the mantle of the Earth, is a tremendous insulator. And the amount of heat being coupled to the surface by that molten core is only about 0.5 watt per square meter. It's negligible. Versus something like 350 watts per square meter coming into the top of our atmosphere from the sun. Some of that is reflected. That's what this albedo is. About 30% is reflected. So about 70% reaches the surface. That's about 250 watts on average over the surface of the globe. That's what warms the planet. This is the Planck distribution describing the wavelength distribution of these visible photons, these little packets of energy coming from the sun. Then the Earth starts to warm, but it doesn't warm without limit. It becomes a warm body itself and radiates just like the star. It's just not invisible, so we can't see it. So it's less intuitive to us. But any warm body, the human body, that's how a passive night vision camera works. It detects these infrared photons. So the Earth warms up until some equilibrium state is reached, where the energy from the sun, now you're accounting for the fact that you're 93 million miles away to get this number, 350, is balanced by the energy being re-radiated by the Earth in the infrared. Total energy is the area under this curve. Turns out you can integrate this Planck distribution in closed form, at least the indefinite interval from 0 to infinity. And each year I ask students to do that, and usually 1 or 2 actually manage to do it. And you get this remarkably simple result, where the energy radiated by a warm black body is proportional to the 4th power of the temperature, whereas sigma here is a constant. It captures all these constants: Planck's constant, speed of light, Boltzmann's constant, and a single Stefan-Boltzmann constant. So knowing the energy input, we can say, let's calculate the temperature of the Earth. So the energy comes from the sun, set that equal to the energy radiated from the Earth. Solve for T, here's what you have. And you calculate minus 17 C. And I was a little disappointed by that because I know you can Google it. The average temperature at the surface is about 15 C. So what's going on here? Close, but 32 degrees off is not very satisfying. Well, there's nothing wrong with the physics, and we'll take a look at that. But do notice that there is only one adjustable parameter in this equation, and that is albedo. This is independent of CO2 concentration, greenhouse effect. Nothing wrong with the physics. Here's a picture which is true to the physics. It's a picture in the infrared satellite picture. And if the continental boundaries weren't drawn in, you would have no idea what you were looking at, because these photons are coming from high in the atmosphere. These infrared photons, it turns out, are absorbed by the greenhouse gases, whereas the visible light coming in is not. And you can look at this temperature bar. The middle is minus 20. I don't know exactly what the average would be, but the middle is minus 20. That's pretty close to our minus 17, which the physics predicts. So the physics predict the temperature of the planet, which means the temperature as viewed from outer space, ignoring the photons reflected from the sun. What the greenhouse gases do is modify the temperature distribution as we work our way down through the atmosphere to the land and ocean surface. You can repeat this calculation for other planets. For Mercury, the predicted number right here, 164, is very close to the measured number, 167. And you'll note there's no atmosphere on Mercury. For Mars, there's virtually no atmosphere. It's less than 1% of Earth's pressure. A 4-degree difference, again, pretty good. Now, Earth has a modest greenhouse effect. It's all due to this trace amount of CO2. But it's enough to create a temperature gradient as we come down through the atmosphere. So 32-degree greenhouse effect for Earth. For Venus, they're wildly different. Here, the atmosphere is almost 100 times as thick as the Earth. It's mostly CO2, and the surface temperature is hot enough to melt lead. But surprisingly, I hope this is surprising, even though Venus is closer to the sun, the temperature of the planet, that is, the top of its atmosphere, is less than that of Earth. And that is because the cloud cover, almost complete cloud cover on Venus, makes it a very bright planet, high albedo. Most of that sunlight is being reflected. But because of the greenhouse effect, the surface temperature is still much higher. But let's develop the efficacy, the usefulness of that albedo temperature control knob. Here's our equation again, Stefan-Boltzmann, solve for the temperature. Back here, this is like a parabola. If we had y equals x squared, we would have a parabola. If we had y equals x to the fourth, it would also be like a parabola, just with square corners. And then you can solve it. You can say, if it's a parabola, you can solve for x and get x equals square root of y. Now you have a horizontal parabola, okay? So that's all we have here. When we solve for temperature, we get a horizontal parabola, just with the corners squared off due to that fourth power. And we're interested in the region around 30%, which is the current albedo of the Earth. It's pretty linear. So we blow that up. What is the slope at the current albedo, 30%? Well, I've taken the tangent line, shifted it down just a little so you can see it goes through 10 here. And then when we get to 30, it goes just about 20. So it's a change of 30 on the rise, a change of 30 on the run. It's about 1 degree of cooling per % change in albedo. That's the temperature control knob, and we can control it. To be precise, It's not quite a degree, it's about 0.9 degrees. Now, this is the mechanism then by which volcanoes historically have cooled the Earth. You think, wow, a lot of heat comes out of a volcano, and yeah, but it's the dominant effect is the reflection of sunlight on a global scale. 1257, the growing season in the Viking Greenland settlements was already on the edge, and this drove them over the edge. Volcanic winter lasting for a decade. 1452, this led where it's associated with the fall of the Eastern Roman Empire. 40 days of continuous snow in China. 1693, Little Ice Age. The unthinkable happened. Scotland, driven to desperation, joined Great Britain. And there are more. Here is anthropogenic, human-induced stratospheric aerosol cooling. This is post-World War II. Some of the most rapid industrialization, injection of CO2 into the atmosphere in history. And yet the temperature held level. If anything, decreased a little bit. Why? There's a nice little cartoon video, which I won't take time to show. But if you go back into these slides, I provide links in the small type and references. The smog over Great Britain and the Ohio coal basin in this country, reflecting sunlight back into space. Again, these smog clouds, you think of them as dirty, but they're really rain. Particles of water will nucleate on almost any solid particle. Grain of pollen, carbon soot, silver iodide nuclei, and it's highly reflective, regardless of the nucleus. So this led to clean air political decisions in Great Britain and in the US under Nixon. The air was cleaned up, and then here's your termination shock. Once you do stratospheric cooling and you stop it, well, yes, the warming then is going to continue commensurate with the CO2 that's present in the atmosphere. And we did nothing to abate the CO2 emissions, so the warming slope was a little greater than it was pre-World War II. So that's what people talk about when they say termination shock. It's not like there's a delta function spike when you turn off the cooling. It's just going to proceed according to the CO2 level. So it is imperative that you work to bring down the CO2 level if we do this. Now, Stefan Boltzmann, sigma T to the fourth, is all you need to calculate the global average Earth temperature. But you'd like a little more detail. Well, Simone Tilms at NCAR Boulder, that's the National Center for Atmospheric Research in Boulder. There are 3 such government-sponsored research labs. The other 2 are in England and in Germany. Lent me this graphic, and you divide, it's like a finite element. It reminds me of a finite element. The atmosphere into cubic blocks, and you have a number of vertical levels. In this particular model, I think there are 26 vertical levels. Yeah. The tropopause, the boundary between the troposphere, the weather layer, and the stratosphere at our latitude is about 8 miles. So 8 miles divided by 26, that's about 1/3 of a mile. So 26 might sound like a lot, but it's only 1/3 of a mile or so vertical resolution. So that's between 1 and 2,000 feet. Horizontally, we're a couple degrees latitude by longitude. That's about 1 Connecticut. So the problem is that's not nearly good enough resolution to model clouds. Clouds are what make everything so difficult, but we do our best. And Ken Caldera, who I mentioned, by the way, Simone was one of our speakers at a computer science field trip, and Ken Caldera was another. Ken and Lowell Wood took this model and applied it to a simulation of the stratospheric aerosol cooling. Now, they were able to simply change the albedo theoretically. So this is not experimental, this is purely theoretical. And the benchmark which most of these simulations are carried out on is a doubling of CO2. Pre-industrial CO2 was about 280 parts per million. Take a doubling of that, you get 560. And we are heading inexorably toward 560. So here's what the temperature would look like with a doubling of CO2. And here's what it would look like if over a 40-year period, you reduced the albedo or increased the albedo by about 2%, or reduced, in this language, reduced the incoming insolation by about 2% over a 40-year period. That is enough to restore basically pre-industrial temperatures. You see this color right here, that's a -1. And at our latitude, it's between 0 and 1 positive. So we have countered, theoretically, global warming due to a doubling of CO2, according to the simulation. And you notice this 2% corresponds very closely to the simple Stefan Boltzmann estimate. We're going to need about a 2 °C reduction. And, you know, right on the money, 2% change in albedo, 2 % change in temperature. Now, with a model, you want to exercise it. And since the Northern Hemisphere is more sensitive to climate change, because there, the conversion from ice to seawater and floating ice and seawater and vice versa is more pronounced. So this seems to be the hemisphere in which climate change is triggered. So since that's the most sensitive, what if we do our insulation reduction, or if we did this in practice, our injection above the Arctic Circle? And so they modified the model so that they could do that. And here's the result there. Now here, since it's above the Arctic Circle where the incidence angle is much higher, and there's not even sunlight to reflect during half of the year, the insulation reduction has to be much stronger. So here's a 10% reduction, here's 50%, 50%, 50. But the model shows that on a global average basis, this would have the same temperature reduction that the globally uniform insulation reduction in the previous slide. The amount would lead to the same complete countering of CO2 warming. And the last result I'm going to show for that model is the Arctic ice cap. This is pre-industrial. This is a doubling of CO2. This is the globally uniform reduction of about 2%, which virtually restores the ice cap. And this is the 50% Arctic injection. Now, in our generation, not yours, but your parents certainly, Mount Pinatubo erupted in 1991. And it cooled the planet by what, I forget the number, about 1/2 degree, I think. It's in here somewhere. Yeah, I think it was about 1/2 degree centigrade, about 1 degree Fahrenheit. Here's the eruption. This is a view from the space shuttle edge on of the orange troposphere, the weather layer. You can see the cumulus clouds and the stratocumulus clouds here and here. Clouds. The white is a stratosphere, and there's this dark, polluted tropopause between the two. That's where sulfate particles from Pinatubo accumulated and reflected sunlight into space, changed the albedo, and cooled the planet. Curiously, we'll look at the healing curve in a moment. It pulled down the CO2 level in the process. And that perhaps was due to the enhanced diffuse scattering, which is better able to penetrate the undergrowth in a jungle or a forest. So it enhanced vegetation growth, and or just the cooler temperatures near the equator. So that was a curious side benefit. Here's the caldera today. I'd love to see it. Normally, that transition between the troposphere and the stratosphere is smooth. Another picture from the space shuttle. Why does material tend to accumulate there? Well, that's the temperature inversion. Because the visible light passes through the atmosphere for the most part and warms the surface, the troposphere, the weather layer, is heated from below. And these warmed air molecules in turn radiate infrared, some of which escapes to outer space. So we have a cooling tendency as we rise to the troposphere. But at some point, the water vapor gets frozen out, the convection, turbulence, the weather ceases, and the temperature inverts. And this is helped along by absorption of the ultraviolet part of the incoming spectrum by oxygen in the stratosphere. It's enough to dissociate some oxygen, and then atomic oxygen can form ozone, which absorbs more UV. So the stratosphere heated from above creates a situation where warm air is above cool air, stable situation. This is why jet planes fly close to the stratosphere. It's much smoother. But if you can inject material there, as volcanoes and humans have done, it will linger for a couple of years, as opposed to a couple of weeks before it rains out in the troposphere.
Wait, hey, Mr. Brucker, there's actually a question
Yes.
in chat if you want to address that.
Okay, great. Let me get tuned in here. Thank you for that. The hypothetical albedo decrease occurs due to an aerosol that will be sprayed in the northern hemisphere. Well, over whose head is the big question. You can inject it anywhere. I think for greatest effect, least loading, you would want to do it at the equator. But this is the global north versus the global south. And who has the power? We will see, but it could be that it's decided to inject over the head of the hapless Inuits, the powerless Inuits. So I think where you inject it and who has their thumb on the thermostat, those are the hard questions.
Oh,
but
may
I will point
ask?
out, follow on to that question, that don't think that this is a local phenomenon. You can't just inject over the Maldives thinking you're going to save the Maldives. It, by definition, is global, because for various reasons, it quickly circles the globe. Yeah. Was someone saying something?
Is the current solution to like mitigate climate change right now is spraying an aerosol, which is meant to decrease like the reflection of, I forgot the reflection of heat. Like, what is the current
the
hypothetical
aerosols do nothing
solution?
more than control the temperature. By mitigation,
The temperature
what I
of
mean,
the Earth?
of the Earth.
Okay.
Now, mitigation to me, what we have to do, the only lasting solution means carbon removal. So the aerosols last time do nothing
How
to
much time?
to the situation, but they can't control the temperature. Does that make sense?
Yeah, so are the aerosols like a temporary solution to buy us more time in order to effectively develop something that would combat climate change in the future?
Precisely.
All right, thank you.
Yeah, and having thought about this for 20 years, I think it's time for us to start thinking about controlling our temperature, period. I mean, yes, nature has taken us through ice ages in the past. Nature has taken us through periods which are much warmer than they are now. But there weren't people around. Now that there are people around, we will not respond well to this. We'll have compassion fatigue after the first few batches of climate refugees. And I do believe we have the technology, the know-how to ward off the next ice age. We may have already done that with our current emissions. And I think we need to take control. We need to co-opt nature's natural rhythm, if you ask me. But I just want to present the physics and get you guys thinking about this. Now, this temperature inversion is critical to everything as far as the implementation of stratospheric aerosols. So we've actually measured this. This is one of our Green Club's Youth for Climate mission. And we launched an instrumented weather balloon, and we actually measured. Here it's plotted in a different way. This is temperature on the vertical and altitude. So we're going up with our balloon. The temperature is going down. We reach tropopause at about 8 miles. And then it starts warming up. And then the balloon bursts by design, and it comes down quickly in a parachute and reverse this process. So we have confirmed experimentally this temperature inversion at the stratosphere. A lot of fun to launch a hot air balloon. This is the picture which stimulated me to do more thinking about this from super freakonomics, the garden hose to the sky. It's lofted by balloons, which are designed so they can be moved without sliding down the whole hose. Pretty long, up into the stratosphere, spritzing sulfates into the sky. And remarkably to me, it was claimed that just 1 or 2 of these would suffice to cool the northern hemisphere. So I checked that out, looked up my mass flow equations, and sure enough, you can pass through a single 2-inch tube where the repeater pumps every 100 feet, 200 PSI, about a megaton of aerosol per year. And we're talking a few megatons to do the job. So I don't know if this is practical, but it just dramatizes how relatively low the required loading is. Especially when you consider the fact that right now, we're emitting about 61 megatons of sulfate per year from burning coal. Pinatubo injected about 11 megatons, it's estimated. Paul Crutzen, the Nobel Prize winning Danish physicist, estimates about 5 megatons per year would suffice to reverse global warming. So in my mind, we have a win-win situation. If we could simply take a small fraction, less than 10% of our current emissions and move them into the stratosphere, it would be a win-win for both. Again, the point is, this is all tropospheric injection. It rains out in a couple of weeks. Tremendous volumes are needed to cool the planet. Moving into the stratosphere, it resides for a couple of years. That was the duration of the Pinatubo effect. So that's a factor of 50 reduction in loading. Again, questions about human health, earthbound astronomy. My gut feeling is there, you might not notice anything. I mean, your parents were alive in 1991. Ask them if they noticed anything when Pinatubo cooled the planet. I certainly didn't. Of course, at other latitudes, there certainly were noticeable effects, but in Beijing, in a big city, you probably wouldn't notice anything. In pristine skies, like you find in the US, it's an open question. And I admit, I don't know what the answer is. Now, this is probably a more practical way to do it. Again, this comes out of NCAR Boulder. They observed that the California wildfires in the last few years injected carbon soot into the stratosphere. And how did it do that? Well, by creating a thermal updraft. Volcanoes would do the same thing. It's not like they're blasting particles like out of a cannon. It's creating a thermal updraft. So they simulated the addition of some carbon black particles to their aerosol. The purpose being to absorb sunlight and create a thermal updraft. And you need a rather concentrated delivery to make this work. It seems that there's some threshold that you need to reach on the carbon black. So they modeled a 10-day injection in June, one 10-day injection each year. And they compared it to, here we go, stratosphere. The light curve here is just stratospheric injection, as we've been talking about, without soot. They compared it to tropospheric injection with soot, carbon soot, and you get a comparable effect. And this is a tremendous practical implication because 747s can fly at this altitude. They did some latitudinal studies as well, but it's the fact that 747s can fly. So they estimate that 335 747s making 6 flights per day over that 10-day period, about 20,000 flights, 2 hours per flight would do the job. 8 runways, a couple of airports close together. Again, you want things to work in concert. You need that threshold soot level. And that was to fly 2 megatons. And for comparison, that's about 1/5 of the annual cargo tonnage. And by the way, we're talking about sulfates only because that's how nature's done it. It's a natural material, but it is not the most effective scatterer. And H2SO4 or SO2 rather is not the ideal precursor. You can use lighter precursors, reduce the loading. And then if you get chemists and engineers working on this, no question, they can come up with much better scatterers. Certainly, an aluminized mylar microparticle with a high dielectric constant is 100 times, 1,000 times more effective as a scatterer. You know, gold is the best reflector of all. But anyway, these are the numbers. I'm talking mainly sulfates today. Another comparison, if we had time, I would ask you, how many people do you think are in the air right now? Well, at any given moment, it's about 500,000. It's equivalent to about 1,200 747s in the air right now. There's some assumptions, average flight length. 6 million people fly somewhere every day, nearly 0.1%. So relatively, this is not a huge cost or technical challenge. That's the point. Now, another thing of note is that the California wildfires occurred in an area of atmospheric descent. we're talking about 30 degrees right here, where there's a downward flow of the atmosphere. So it looks like the solar powered lofting could work at any latitude. It's strong enough to beat the natural circulation. I think for maximum effectiveness, if we did this, we would probably inject at the equator. At the equator, we have a situation where the hot air is rising, warm, humid air. Eventually, the moisture freezes out. The air starts to move toward the poles, displace cooler air. The moisture rains out, and this air comes down bone dry around the mid-latitudes. This creates the Gobi Desert, the Sahara, the desert southwest US. The boundary, the tropopause, is about 11 miles at the equator, 11 miles, 8 miles, 5 miles at the poles. So the higher you inject, the longer it lasts, the lower the loading. And the natural circulation spreads it latitudinally. And if you can take advantage of the jet stream, you can spread it longitudinally as well, get good dispersion. So yeah, we're almost done with stratospheric aerosols. Now, for sure, sulfates and sulfuric acid is not good for the ozone layer. Pinatubo was not good for the ozone layer. He's recovered, but David Keith at Harvard has investigated calcium carbonate. That's a basic material. And the point is, I'm not a chemist, but it can neutralize acids apparently from our anthropogenic emissions, and not just reduce the degradation of the ozone, but perhaps enhance it. So here are the modeling results, which are all we have to go by right now. No experiments. Experiments have not been allowed, but the curve going up, that's good. This is the calcite. This is the sulfate. So again, turn good chemists, material scientists loose on this problem, and certainly we have a chance to impact this ozone problem. Apparently, there's some stratospheric warming that occurs at the same time that we're doing this stratospheric injection. I'm not enough of a chemist to understand that yet. So I certainly don't have all the answers. Now, again, no experiments. Gosh, years ago now, the Harvard group, David Keith and Frank Koich, proposed lofting a few kilograms of material, a few hundred grams of material on a balloon. They'd like to use their calcium carbonate material, turn the balloon around and fly back through the mist and analyze it. Really, it's more of an experiment in changing social norms than it is in doing a real experiment. So they're trying to do it right, total transparency. And it's taking time, it still hasn't happened. And I understand, I haven't talked with David Fahy at NOAA, but he has some funding to actually do the stratospheric aerosol injection. I'm not aware of any progress there. There has been experiments around cloud brightening. That's ongoing, but in the troposphere, anything that you do requires tremendous amounts of material. So here we are, we're halfway through. This was our original roadmap. We're through with the theory and the practice of SRM. And in the time that we have, let's do a reality check. Why it's going to take quite a while to mitigate CO2. Understand the greenhouse effect a little bit better, the positive feedback, and consider the rising sea level. Now, CO2 in my lifetime has gone from 350 to 420 parts per million. Seems like a lot, but when you express it as a percent, it's 0.03% to 0.04%. That is not a lot to make forward-looking projections on. And I cringe when I see every mishap, floods and fires attributed to climate change. I'd be careful about doing that. It can make the science look bad. I believe the largest forest fire in California or on the West Coast actually happened in 1905, before humans had pulsed the atmosphere with CO2. So be careful. I believe tree rings indicate there have been 80-year droughts in our history. So please be careful. Well, one thing we can learn from is this thought experiment where we just remove CO2, take it to zero from the atmosphere and see what happens. And what we see is a spectacular decrease in temperature. That's this black curve from our nice balmy 15 degrees C where we are now to about minus 20 in just 20 years time. That's still remarkable to me. This trace amount of CO2 is the second temperature control knob for the Earth. It's a trigger. It triggers positive feedback, which really makes the big effects. Now we end up minus 20, a little colder than our Stefan Boltzmann number of minus 17, because positive feedback kicks in. Dark seawater is replaced by reflecting ice, and our albedo, the orange curve here, goes from, 30% to something like 40%. And the temperature change, which we see, is used to infer this roughly 4x positive feedback effect. You can calculate the radiant forcing due to the CO2 and the temperature change that would involve. And the actual temperature change is about 4 times that. This provides a nice reinforcement of that positive feedback factor of 4 times. This is going back in time where we infer temperature through this deuterium to hydrogen ratio. That's a temperature proxy. This is measured in ice bubbles in Antarctic ice cores. And we see a correlation. Each of these peaks is about 100,000 years apart. We can go back about 500,000 years by drilling into these Antarctic ice sheets. And we see a correlation with the CO2 level. It's a complicated picture. I managed to get myself quite confused. But talking with Andy Melnick, he's in a group at Oregon State University up in Corvallis. They actually have traveled to the South Pole. I've actually held one of these ice cores in my hands. And as he understands it, the last ice age, for example, was triggered by a change in our orbital parameter around the sun, in particular our tilt. And this led to a slight cooling in the northern hemisphere. That in turn triggered the release of CO2 as the oceans gradually warmed. I guess we're coming out of the ice age. Coming out of the ice age. A slight increase in solar insolation in the northern hemisphere triggered a warming of the oceans, especially the Southern Ocean, which released CO2. So temperature rise preceded CO2 rise in the northern hemisphere. Then the rising CO2 in turn triggered a temperature rise in the southern hemisphere. So you get a different sequence depending on whether the ice core is from Greenland or from Antarctica. So just a point of interest as we go along here. But more importantly, following this last transition, transition out of this interglacial here, expanding just this part. By the way, here's where we are today. We're higher this little red dot, higher than any time in the last 500,000 years for CO2. Expanding this region right here, we can see the rise in CO2. Methane is also part of this. And we can look at the change in temperature. The radiative force induced simply to the greenhouse gas is this number right here. And the predicted temperature rise is about 1 degree. This is about 1% of that 250 watts of incident radiation. And it leads to about 1 degree predicted. The actual change about 4 or 5 times that. So again, positive feedback to 4 or 5. It's confirmed or supported by the ice core data. Now, here is CO2 versus time. The Keeling curve started in 1958 by Charles Keeling, the most important curve in climate science. And there's been a lot of talk. Embarrassingly, we walked out of the Kyoto Protocol in 1997, and we were sort of a quiet participant, did not receive the implorings from the contingent from the Maltese to have a meeting. And so all this talk, quite figuratively, almost literally, is so much hot air. In the meantime, transformation of large parts of Asia. China has become the manufacturing center of the world, increasing industrial activity in India. It's been a total rout for free market capitalism. And I don't see this rolling over anytime soon. When COVID came along, I got all excited, as did my students. Let's see if we see a change in the scaling curve. There's virtually nothing to notice. In spite of the fact that I didn't drive very much for 2 years, but the world is heavily addicted to oil and coal. So I think this is important enough. Each year we plot this in the classroom, and Joshua, Brian, Jessica, if you're here, I don't know if you're in this crowd. But there's a result. If you're curious as to why it oscillates on this annual basis, you can ask Brian or Joshua. Well, we certainly have our work cut out. This is what you guys are all about today, to pull the CO2 out of the air. But given the recent history, we can look at the gain each year converted to a percent. It's about 0.8% increase each year, and treat it like an interest rate. So here's the interest rate formula with our interest rate. And in another 42 years at the current rate, increasing about 2 parts per million per year, we can expect to see the doubling in another 42 years, around 2100, thereabouts. Root cause is population. The more people there are, the more people that like to fly. You know, we're never going to fly on battery power. At least not passenger jetliners. New pipelines coming online. Are you aware of the pipeline from Norway to England? These are massive, 4 feet diameter natural gas tubes, remarkable engineering feats. This is to supply nearly half of Great Britain's energy needs. Billions of dollars, tens of billions of dollars, and you can be sure they want to get their money back. 40-year lifetime expectancy. Let's see, more pipelines coming out of Siberia. Japan is spooked on coal, or spooked on nuclear, 22 new coal burning power plants. Nigeria's population is projected to exceed ours mid-century. Typically about 75,000 fires are burning in the Amazon at any given moment. Let's not get depressed about this. There are solutions. Well, let's face reality. Don't Don't get caught up in wishful thinking. And don't suffer severe end sickness like I did 20 years ago. I had, end sickness. Situation seemed hopeless, but it's not. So that's why I'm doing what I do. Yeah, let's one last quick look at our atmosphere from the side. It's both perilously thin. We are able to modulate its outgoing infrared absorption capacity. But again, it's vast. Once the CO2 is dispersed over this incredible volume, it's hard to pull it out. It was easy to put it there. The amount of CO2 that we have injected is equivalent to filling Lake Erie, say, with gasoline and setting it ablaze. Or for our West Coasters, about 3 Lake Tahoes, fill it up with gasoline, set it ablaze. Relatively easy, relatively quickly, we have done that. Once it's dispersed, it's not going to be easy to pull it out. Well, these numbers keep changing. It's hard to keep up. The average carbon footprint per capita worldwide is about 5 tons per person, I believe, today. Nature's ability to absorb is about half that, about 2.5 tons. One of the reasons I re-careered because I was self-conscious about all the traveling, but my footprint is still about 28 tons. Each year I have my students take a form home for their parent to fill out, and the average mission parent footprint is in mid-30s, as high as 50, say. Depends on how much jet plane travel, how many trips to India or China. The average American carbon footprint per year is 17 tons. So you can see it's a long ways to 2.5 tons. Anybody want to guess what the, among modern developed nations, the country with the lowest per capita carbon footprint is? Which country? I'll give you a guess. It's a large European country. What's the largest European country?
I mean, like Russia, right?
Russia, okay, next year, largest. Keep going, give me a few.
But you said large European countries, right? So like
Yeah, just large countries in Europe. UK.
Yeah, and
Keep going.
I don't know, like Finland, Norway, Sweden.
Norway, France.
Oh,
France is the
yeah.
one.
Oh,
Now,
France,
why
okay.
the per capita footprint there is about 5 tons. Do you know why? How do they generate their power?
Through
Like wind and solar?
That's just a drop in the bucket so far.
yeah, most of it's just through fossil fuels, right? Right, I guess.
It's nuclear.
Oh, nuclear, okay.
50 nuclear plants. So I'll admit I like nuclear. Can be done much more safely. But let's not go there right now. Let's get back to the problem at hand. Another gut check here. This is modeling that my students do using something called ModTran. It's a program, browser-based, administered by the University of Chicago, widely used. And you can do things like this. You can calculate the projected ground temperature due to so much CO2. So here we are today around 420. And we've come up, we've gone through this we're on this plateau. And going from 420 to 560, now we're not doing much as far as radiative forcing due to the CO2 itself. Positive feedback, on the other hand, is doing a lot. But once we start to pull the CO2 down, we're still on this very shallow slope. Won't have much of an effect compared to the positive feedback. So it's not just a matter of turning that Keeling curve over and pulling it down. You wouldn't see much of an effect until we get way down to this knee effect. So that's what we're up against. Now, I'll point out along the way, advocates of research on methane, which is something we also have to worry about, like to say, oh, methane, it's 80 times more potent. That's why it's the most important. Well, that's only because methane is on a steeper part of its curve. The methane is only there at about 2 parts per million. It reacts. Its lifetime is only 10 years or so. CO2, it's there indefinitely. This is what we use to carbonate our beverages. It's not reactive. So the methane is simply on a steeper part of its curve, and a small change in methane concentration will lead to a much larger change in radiative forcing. But CO2 is the stronger gas. It's the one, well, it's the only one we need to worry about, the only one I'm going to worry about today. How are we doing? Pretty good on time. And don't be disillusioned by the time it takes for the science to be heard. I went through this starting at Eastman Kodak. We were recording electronic images on floppy disks in 1984 and printing them out on thermal media with a quality that was every bit as good as silver halide. But the powers that be at Kodak, where the profit margin for silver halide film was comparable to that of marijuana. I mean, it was a cash cow. It was Kodak and Fuji. It was just too good to be true. And they were not willing to cannibalize the silver halide industry for the electronic image capture. It's a lot like the Swiss watch companies who had LCD and quartz microbalance technology, but couldn't make the change. Well, Kodak abandoned my patents. That's what led to my move to the West Coast. I wrote a book chapter and a Seagate manager read it and wanted to pursue magnetic recording for electronic image capture. And finally, in about 2004, when I transitioned into teaching, it became a manufacturing reality. Today, all magnetic media is so-called perpendicular magnetic recording. That's what I was working on. It took about 20 years. So don't be disillusioned. It's going to take time. But if maybe, 10% of us Americans can see the light, that'll be enough to shift the balance. But I've painfully watched our administration redact or change the wording of scientific reports and cast doubt on the science and tweet that the fact that you can make a snowball disproves global warming and so on and so forth. Ultimately, the good technology wins out. And if there ever was a time when we need the good technology, it's with the climate. Now, this is sea level. Now, I'm not here to claim that this is human induced. Whatever the reason, I would still be promoting awareness of the stratospheric solution because sea level is rising. Most likely it's due to global warming. And if it is, by the way, about half of the rise is due to land-based glaciers melting into the ocean. The other half is due to thermal expansion of the liquid water. But anyway, here's a curve, and I've tried to estimate the slope for a recent period, and I get about 3.5 millimeters per year. That's about an inch every 8 years or so, about a foot every 100 years, something like that. And again, it's hard to keep on top of these numbers. You should Google this. What is the rate of sea level rise? I did that at the end of the last school year, and there seemed to be a consensus that it's more around 5 millimeters per year. So I think it's increasing, but I'm not sure. But anyway, that's why I say the Maldives have about 100 years. Maximum elevation 3 feet. Things like gravity feeds, sewage disposal are going to stop working with another foot of sea level rise. This is another place I would love to visit, spew more CO2 into the air in the process. Idyllic. Miss Rusu, math teacher from Mission, has been there. She describes the marvelous white sand beaches. There's a restaurant which you can get into and it submerges and you can watch the sea life as you eat. For a while, they were buying land in Australia. They are resigned to mass migration. Now I understand they're dredging sand from the ocean and creating artificial islands. In the South Pacific, the Marshall Islands will disappear even sooner. Tuvalu, Solomon Islands. This is the Louisiana Delta. And not just because of rising seas, but because of Mississippi outflow mismanagement. The Delta has been deprived of much needed sediments. This is all spearheaded by big oil and controlling the flooding on the lower Mississippi. Tremendous expenditures by the Army Corps of Engineers to dam the Mississippi. And again, co-opt nature's natural rerouting of the river. But, you know, there used to be a lot of yellow land in 1940. Today, it's mostly blue ocean. And the Choctaw Native Americans are being forcibly displaced. They don't want to go. And it's expensive, an expensive proposition. Turns out it's several $100,000 per person to do this. It's expected that these folks, where are we, back in the South Pacific, will be the first official environmental refugees due to rising sea level. Although it's already happening again in Louisiana and in the Alaska and Aleutian Islands. I was talking and meeting at the University of Central Florida in Orlando. Did you know that's either the largest or the second largest university in the country? I didn't even know that, but they are very concerned. Large climate science department. Here's Miami after 6 feet of sea level rise. It's more like an archipelago. So you turn into the talk shows and the callers who are high and dry say, well, these dummies shouldn't locate along the coast. They're just going to have to move. Don't think that's realistic. That would destabilize the whole world. Bangladesh, I believe most of southeastern Bangladesh is on the Brahmaputra Ganges Delta. And the highest point is maybe 7-8 meters. So that coastline is going to recede very rapidly. I read a book by Gwen Dyer, Climate Wars, and he looks for various flashpoints. And one place he looks is the border between Pakistan on the other side of India and India. Apparently the headwaters of the main source of water, main river in Pakistan, are controlled by India. So what's going to happen if water starts flowing out of the Himalayas from melting glaciers? And he just wants to think about the possibility of a nuclear exchange. We have two nuclear powers there. As things heat up, and perhaps a unilateral implementation of solar radiation management. It's cheap enough so that some rogue nation, even some rogue individual, could do it. It's not how we want it to happen. We want to do it the right way. So I'll give you some passing metaphors and then I'll be wrapping up. Glad to have some discussion if you like. Let me give you a closing analogy. If you were to climb a 100-foot flagpole, say, and drop a leaf, and down below in the plaza, it's laid out on a grid with, say, 10-foot squares, concrete squares, all right? And I ask you to tell me which square is that leaf going to land on? I would claim that all the computing power in the world could not with any certainty tell me. After all, it might depend on the fact that some coal-fired plant 100 miles away just fired up to meet air conditioning demand 24 hours ago. That's an initial value problem. That's like predicting weather. It's incredibly sensitive to initial conditions. On the other hand, if I asked you, give me the distribution of the thickness of the pile of leaves after I've dropped 1 million leaves, you could do a very good job. That's a Gaussian, that's a bell curve. That's a boundary value problem. That's what I've tried to focus on in my discussion today. Global temperature is a boundary value problem. Weather is an initial value problem. So it's not fair to criticize the disagreement in the models. They're not to the point where the resolution is small enough to deal with clouds. But we're learning. If you want a challenge, there's a good one. Now, I don't think there's any question, second main point in closing, that mankind, you and I, can control the temperature up or down. It's probably easier to cool it down, although perhaps there are other ways to warm us up. I mean, when I was your age, school was not regularly, but a few times each winter closed down. Oh, we'd wake up and so excited to hear on the radio that school was closed for the day. And there was concern that we were entering another ice age, a little ice age. And there were thoughts about spreading carbon soot on the Greenland ice cap. I'm sorry, I've gone over time here. I better stop. We could find our ways to warm ourselves up. Point is, think of the climate as an ornery beast which overreacts to the slightest nudge. The nudge is variation in solar radiation, variation in CO2 content, and then positive feedback kicks in. So there's no silver bullet here. Rather, there's silver buckshot. That's what you guys are doing. That's what I was doing when I worked to get LED lights in the N wing at our school. Solar radiation management is a rather large calibration pellet, large caliber pellet. So all these things working together. So listen, here's what we covered. It was to jog your memory. I'm glad to have some further discussion if you still have the energy. Thank you so much. Great honor to have this opportunity. I'm sorry for going over time.
Thank you very much.
Okay.
Yeah, definitely. Thank you so much, Mr. Brucker. We really appreciated your lecture today, and yeah, we learned definitely a lot. Are you comfortable in sharing the slides? I know that there might be some people maybe who didn't attend this meeting might be interested in like looking over your slides.
Yeah, absolutely. They're not on our website. I don't have my website since I've left Mission. Can we work out a way to do that? But absolutely, yes.
Okay, yeah, that sounds good. I guess we can deal with that a little bit after this meeting.
Okay.
But yeah, I would like to thank you again for coming today. It's definitely a great guest lecture, and we definitely learned a lot about climate change and how to solve it.
Okay, and I thank you for your contributions last year, Joshua, Brian. All right, you guys take care.
Yeah, thank you so much, Mr. Brucker. It's been great having you here.
Okay, guys.
Thank you.
Thank you guys for coming.
Bye.
Bye.